Welcome to this lesson on sliding mode control for mobile robots by Manchester Robotics. Let's start by considering a double integrator system with a feedback control law given by U equals minus k times x, where k is a positive scalar. The state space representation can then be obtained as follows. Let the gain k to have a value of 0.5. The phase portrait of the system can be then depicted in the figure. We can see that the evolution of the system encircles the origin in the shape of an ellipsoid. We can observe that the vector field points in the same direction. The system is said to be Lyapunov stable, but not asymptotically stable, since it doesn't evolve towards the origin. Let us now change the value of the gain k to be 3, just for the sake of this example. We can see now that the evolution of the system has changed to be a vertical ellipsoid encircling the origin. As in the previous example, it can be said that the system is not asymptotically stable. We can take advantage of both behaviors by selecting the ones that makes the system come closer to the origin. To this end, we can use the following control law. This control law selects the gain of 3 for the top right and bottom left quadrants of the phase plane, and a gain of 1 in the other two quadrants. We can see now that the system evolves towards the origin, fulfilling the asymptotical stability condition in the sense of Lyapunov. We can also observe the switching of the controller by looking at the vector field in the figure. We can take this idea even further by implementing a relay or switching function S. In this case, let the function s to represent a line on the plane with a slope mm equal to 2. Let us be reminded that the line is the intersection of a hyperplane with the plane. The positive values of the hyperplane lie to the right of the line, and the negative values are to the left of the line. Let us implement the previous control law, but now using the switching function ss and its positive and negative values to select the gain. We can see that the function s acts as a switch every time the system changes from positive to negative. Furthermore, we can observe that the system is asymptotically stable since its evolution slides to the origin, and it presents a phenomenon called chattering, which are high-frequency oscillations due to the relay function. By increasing the gain k of the controller, the system slides to the origin in less time with increased chattering. We can also play with the slope m of our sliding surface to improve the behavior of our controller. A series of questions now arise. How can we use this type of controller on a mobile platform? How can we design the controller and prove its asymptotic stability? Is this type of controller robust? Want to find out? Join us in our advanced robotics courses at Manchester Robotics.